In the temperature range required for welding, the reaction of metals produces a number of problems. At red heat, metal has a strong tendency to combine with oxygen in the air. Also, most other gases which may be present, such as hydrogen and nitrogen, as well as water vapor, may combine with the molten metal. These reactions result in a change to the metal's chemistry, producing a poor weld, or making it impossible to achieve any weld at all. It is necessary to exclude these gases from the work area during the welding operation. This can be done by using a shield or cloak of inert gas. An inert gas will not react with the heated metal. It forms an envelope over the work area and around the electrode during welding. One of the most versatile methods is known as metal inert gas welding, or MIG. This process has been used successfully in the welding of mild steel, stainless steel, aluminum, magnesium, and many other hard-to-weld materials. Heat for this process is provided by an electric current. The filler rod is a consumable electrode fed automatically. The arc is shielded with a constant supply of inert gas. Argon, a heavier-than-air gas, or helium, a lighter-than-air gas, are frequently employed. In MIG welding steel, carbon dioxide is often used. It is not an inert gas, therefore the welding rod must contain a deoxidizer. There are distinct advantages to the MIG process. High welding speeds, less distortion, increased mechanical properties, greater resistance to corrosion, and lower welding costs. Electricity is supplied from a direct current power source. This combination TIG and MIG welder provides the required current and a virtually constant supply of voltage. Voltage can be preset. The amperage is governed by the rate of wire feed. The wire electrode is supplied on spools. It should be kept clean and kinking and scratching avoided. The size of spools may vary from 1 to 25 pounds. The wire is threaded through the feed mechanism and cable to protrude from the gun nozzle. This machine has feed rollers in the gun which pull the electrode wire through the cable. The wire is pulled at a predetermined constant rate, which also automatically controls the amount of current to the wire. With this type of constant voltage machine, there are no feed rollers in the gun. Instead, external feed rollers push the wire through the cable at a constant rate. This welding gun has a small spool of electrode wire mounted inside. It has the advantage of quick spool change and shorter travel for the electrode wire, thus reducing the possibility of fluctuations in the wire feed. MIG welding employs intense heat. A cooling system is needed to prevent damage to those parts of the gun close to the arc. Coolants may be filtered water, a mixture of water and soluble oil, air, or in some situations, antifreeze. When welding, the coolant is circulating along cables through the welding gun. The gas cylinder is equipped with a regulator and flow meter. Electricity, gas, water, and wire are carried to the gun through these cables. The trigger switch initiates all supplies and controls. A ground wire from the power source is clamped to the workpiece, which is then negative, and the contact of electrode and workpiece completes the circuit. There are 3 different types of power supplies used in MIG welding. A source common to MIG, TIG, and stick electrode is the constant current type. This supply produces a virtually constant current because of steeply drooping output characteristics. This graph shows the volt-ampere relationship for this type of power source. Note that there is very little change in current for a 10-volt fluctuation. This source is primarily used for stick electrode welding. The air-cooled 1-pound gun is generally used for welding relatively light-gauge metals. In this case, the arc voltage is controlled by the wire feed rate. Current is preset at the control panel. The constant voltage power source is designed to give a variety of current values at the arc without significantly changing the voltage requirement. This volt-ampere graph has nearly flat characteristics. This system has the advantage of providing the greatest degree of self-adjustment so as to give a steady arc length during welding. With the arc voltage and wire feed rate selected, the current rises to a value where it consumes the wire at the preset rate of feed. To raise the current, the wire feed rate is increased. The constant voltage system has the advantage of reducing burn back so often encountered with the dropping voltage constant current system. Another type of supply uses a rising voltage method. A high current density over a narrow weld area produces a better weld. This heat concentration in a narrow area will enable you to weld faster with less distortion because of the smaller heat zone. Low currents are used for short-circuit welding of steel, and higher currents produce the fine spray essential to spray welding of aluminum. Pressing the trigger on the gun operates the coolant and shielding gas valves and the primary contactor, which are located in the supply unit. As the wire electrode touches the work, the arc is established and the wire is fed from the gun. This is called a scratch start. To stop, the trigger is released, shutting off the shielding gas and coolant. The circuit is also broken at the primary contact. With the running start method, as the trigger is depressed, the shielding gas and coolant start to flow. The wire feeds out immediately, and the primary contactor closes. As soon as the wire touches the work, the arc is established. A running start is best employed with a constant voltage type machine. A stub burn-off control prevents the wire from freezing into the weld pool by keeping the primary contactor closed for a few seconds after the wire feed stops. The wire drive mechanism should be adjusted to ensure a constant rate of feed and a minimum of marking and scratching. Select the correct type of wire for the job and the proper drive rollers for the size and type of wire. To strike the arc, press the trigger and bring the cup of the gun to within a half an inch of the work. The stick out is approximately 3/8 of an inch. For simple butt joints to be made in a flat position, hold the gun at 90 degrees to the workpiece. T-joints and overlap joints made in the horizontal position require an electrode angle of about 45 degrees. The forehand angles are usually 10 to 15 degrees. When pieces of unequal thicknesses are butt joined, slant the electrode toward the thicker piece to obtain equal melting. In general, fillet and lap welding of aluminum requires more current than butt welding. But in both cases, if the current is too low, globular transfer takes place instead of the desired fine spray obtained at higher amperages. Another problem is burn back. To avoid it, make certain that the wire is level wound on the spool. Be sure that the drive rolls are adjusted to the right pressure. Apply enough pressure to the drive rollers so that the wire can be just held back by the operator's gloved hand. In performing a simple butt weld on aluminum, a permanent backing strip may be necessary due to the deep penetration of the MIG arc. The backing strip is of the same material as that being welded. The two edges of the joint must be fused to the backing strip. This is achieved by leaving a larger than normal root opening. Temporary backing strips are made from steel, stainless steel, or copper. These strips are removed after welding, and the joint is back chipped to sound metal. The resulting V is filled with a light bead. The single V with a root face allows penetration while the shoulder or flange reduces burn-through. A temporary backing strip is used. The feather-edged single V aids fusion into a permanent backing strip. The double V does not need a backing strip, but back chipping is necessary. This method is used for thicker metals. When performing a feather-edge single V weld with a backing strip, fine filler wire of 3/64 of an inch is used. The fine wire produces a narrow bead and gives deep penetration. This also means that less material is deposited to make the weld. To avoid a cold start, a backstep method is used. The arc is struck 1/2 to 1 inch ahead of the desired beginning point and then moved back to the beginning of the joint. The short backstep may contain porosity, and so this is remelted as the proper weld proceeds. When welding in a flat position, the forehand gun angle should be 10 to 15 degrees, permitting the operator to see the molten weld pool. The first pass lays down a bead with as much metal as can be controlled for adequate penetration and fusion. The bead should be wire brushed in preparation for the final pass. The danger of undercutting can be minimized by reducing the current for the final or finishing pass, or by increasing the welding speed. The final pass can be made using a slight weaving motion to produce a good bead. T-joints are welded using the fillet technique. This is a horizontal vertical fillet, also known as the standing fillet. Tack the one side, then the other. The position of the electrode during the weld is extremely important. The 45-degree angle distributes the weld metal evenly on the vertical and flat plates. Close attention must also be paid to the current setting if adequate penetration is to be obtained at the root of the fillet. High current spray arc welding produces a deeply penetrated fillet weld. In fillet welding of metal more than 3/16 of an inch thick, the torch moves along the joint with slight weaving motion. This motion agitates the puddle and helps to eliminate porosity. With thicker metals, a multi-run fillet weld is used. Because of possible overlap, the welds are made from the bottom up. These are examples of poor welds. In this case, the fillet is excessively concave. This could mean poor fusion at the root of the weld. This weld shows porosity. And this one overlapping. A good fillet weld will have equal leg length, a well-penetrated root, and a slightly concave face.